we started discussion on natural or free convection. Natural or free convection. So we started by looking at the example of a fluid which is placed in a box, and we looked at the differences in the temperature which leads to density difference, and that leads to a convection. So supposing if T1 is less than T2, we said that rho 1 is greater than rho 2, and therefore the heavier fluid is sitting on top of the lighter fluid, which is an unstable situation, and so that's going to set up a recirculation. Leading to convection. Leading to convective mode of heat transport in the horizontal direction. This recirculation, so that is correct. Right, the driving force is gravity here. Okay. Now the gradient in the horizontal direction, because of the recirculation, not every location in the horizontal direction is going to be maintained at same temperature. So there will be heat transport in the horizontal direction too, but the primary driving force for convection is in the vertical direction because of gravity. Gravity is the driving force. Okay, so now we said that suppose if we have a plate which is maintained at a certain temperature, and then it is suddenly dropped into a quiescent fluid, which means U is 0 and T is some T infinity, and then it results in a certain boundary layer, and we looked at the X momentum balance, in the boundary for this problem, which will be U, supposing if this is Y direction and this is X direction, and U and V are the X and the Y component velocities. So we said that U du by dy plus V U du by dx plus V du by dy, that's equal to minus 1 by rho dp by dx minus G dy square. Okay, so that's the X momentum balance. Now this equation is valid at every location in this problem, and so it is valid in the quiescent medium as well, in the quiescent fluid as well. So this equation is valid both in boundary layer and in bulk. Okay. So now if I look at the equation in the bulk, we know that U and V are 0, the velocities are 0, and not just that, all the gradients are 0 in the bulk stream. In the quiescent region, U and V are 0 because the fluid is not moving, and also du by dy, du by dx, they are also 0. All the gradients are negligible in the quiescent region. So therefore, the X momentum balance simply reduces to minus 1 by, if rho infinity is the density of the fluid in the quiescent region, so that will be dp by dx equal minus G equal to 0. Okay. So from here you can say that dp by dx in the quiescent region, that should be equal to minus rho infinity into G. Okay. But there is no external forcing, which is actually, there is no force convection. So the fluid is not being forced to move at any location. So therefore, the net pressure gradient that the fluid experiences in the boundary layer should be equal to the net pressure gradient that the fluid experiences in the quiescent region, because the fluid is not being forced to move at all, it is actually at rest, and so the net pressure gradient in the boundary layer should be equal to the net pressure gradient in the quiescent region. Okay. So now if we incorporate that into our momentum balance, so what we will see, incorporate that into the momentum balance, we will see u du by dx plus v du by dy. So now I am writing the momentum balance in the boundary layer. Okay, so that should be equal to minus rho infinity minus rho plus nu into d square u by dy square. So this is nothing but the difference in the density delta rho, which is the difference in the densities in the bulk and any location in the boundary layer divided by the density in the that location in the boundary layer plus nu into d square u by dy square. So now if we know what is delta rho by rho, we are done, right? We should be able to solve the equation. So what's the relationship between the density gradient and the other system variables, for example velocity or temperature or concentration, whatever. So here we are not looking at mass transport, let us not worry about concentration for now. So what is the relationship between delta rho by rho and u, v, x, y, temperature, etc. So that is the new variable or new body force term that we did not see so far in all the convection topics that you start seeing in natural convection. Okay. So any thoughts on how do we find this? Yeah, compressibility. So we said that the driving force, so note that in natural and free convection, the density gradient is a function of temperature, right? We said that the temperature difference is causing the density gradients and therefore they have to be related in some way. So far in all the cases that we looked at, the momentum boundary layer equation did not have any temperature dependence. It was independent of the temperature and concentration. So now we will start seeing dependence of temperature on the momentum boundary layer equation. Okay. So the way to do that is what's called the compressibility factor. Compressibility factor. So the typical symbol that is used is beta. Okay. Now the definition of compressibility factor is minus 1 by rho d rho by dt at constant pressure. Okay. So that is the definition of compressibility factor. Now what do you expect the density gradients to be? Is it expected to be very large compared to the density, the local density or not? So it is not, because it is a free convection problem, there is no forced convection, and so we expect even the boundary layer thickness to be significantly smaller, and so we expect that the density gradient also to be very, very small. So therefore we can approximate this as minus 1 by rho So this approximation is what is called as Boussinesq approximation, after the person Boussinesq. Approximating the gradient, the density d rho by dt as simply the differences in the bulk and the local density divided by the difference in the bulk temperature and the local temperature. That is what is called Boussinesq approximation. Yes, Saransh. That comes from the relationship between the pressure gradient in the quiescent region. So if you write the momentum balance in the quiescent region, where there is no velocity, velocity is 0 because the fluid is at rest, and the velocity gradient is 0. So therefore you will see that the x momentum balance will simply reduce to the pressure gradient in the x direction should be equal to minus rho infinity times gravity. and because there is no external forcing, the gradients have to be equal in the boundary layer and the quiescent region, and therefore you replace the dp by dx with minus rho infinity into g, and that's how you get this expression. Okay. Yeah, but there is no flow of fluid, right? So the pressure gradient is going to be very, very insignificant. Yeah, right. But that's already taken into account. Rho into g is already taken into account. The body force accounts for the force that the fluid is experiencing because of gravity. That's already accounted for in the momentum balance. See, we look at only steady state case here in all these courses. There is very little dynamics we look at. The only place where we looked at some dynamics was in conduction, where we looked at the semi-infinite slab. We're really not going to look at transient cases in these kinds of problems. So this approximation is what is called as Boussinesq approximation. Now just to get a feel of what this compressibility factor, really how it plays an important role, is that the compressibility factor, obviously it's a function of temperature. Compressibility factor itself is a function of temperature. Okay. Suppose if we say it's an ideal gas, so rho is given by P by RT, okay, for an ideal gas. Okay. So now from here we can write that beta is minus 1 by P by RT into d rho by dt at constant pressure. Okay. So that will be P by R T square with a minus sign. Okay. So that will really scale as sort of 1 over temperature. Okay. So our compressibility approximately scales as 1 over temperature, but let's for the moment assume that beta is now a measurable property and it's not varying significantly in the temperature range that we are looking at. Okay. So it scales as 1 over T. Okay. So you must understand this difference. It scales as 1 over T, but just for sake of getting insight as to what's happening in this problem, let us assume that beta remains almost constant in the temperature range that we are looking at. So now, we can write now all the balance equations in the boundary layer, and so the first one would be continuity equation. That's the continuity equation. Then we have the momentum boundary layer equation, boundary layer momentum balance. So that will be u du by dx plus v du by dy. That's equal to rho infinity minus rho by rho. So that we can replace using the compressibility factor. So that we can rewrite as beta into T minus T infinity into gravity plus nu into d square u by dy square. So all I have done is I have just replaced delta rho by rho with the compressibility factor expression using Boussinesq approximation, and then we have the temperature balance. Okay. So we assume that there is no energy generation, etc. So this is the energy balance, we have the momentum balance, and we have the continuity equation. So we need to find a way to solve these set of expressions in order to find the heat transport coefficient. Remember that the objective is to find the local heat transport coefficient. That's the objective, and of course the average heat transport coefficient, either at any length or based on the length of the full plate. Okay, that's the objective. So we have to solve some of these equations in order to find the heat transport coefficient. Remember that if we know the gradient at the wall, we are done, right? So heat transport coefficient, because the temperature of the plate is constant and the bulk temperature is constant. So if we know the gradient at the wall, we are done. So the objective is really to find the temperature gradient at the interface between the plate and the quiescent fluid. So I mentioned in the last lecture that we're going to look at the reference velocities for this kind of a problem. So the first and important issue is that there is no bulk or free stream or any other reference velocity There is no reference velocity for this problem because the fluid is actually at rest. We don't know any velocities inside the boundary layer. So what we are going to do is, we are going to assume that there is some reference velocity. We are going to show later that we will not be using this reference velocity for any of the calculation purposes, in fact to even define any of the domains. So the only place where we will be using this reference velocity, so it's an unknown reference velocity. Okay. Now the only place where these reference velocity plays an important role is when you want to make an important decision whether the free convection or a forced convection is playing a dominant role in a real problem. So here we have assumed that the problem is only free convection problem, but in principle, even when you are going to drop a plate inside, there is going to be some disturbance of the bulk fluid, and so you would expect that there will be some velocity. So the question is, how do I decide whether for a given problem it's the free convection or the forced convection which is the dominating mode of heat transport? So it is at that situation where this unknown reference velocity will play an important role. And in fact, in that situation, this unknown reference will simply be equal to the bulk velocity itself. To decide whether forced or free convection is dominant. We will see that mostly before the end of today's lecture as to how to decide which one is dominant and how to decide particularly which correlations to use. Okay, so suppose we use this as the reference velocity and then we introduce the dimensionless quantities. We introduce the dimensionless quantities as x star is x by L, y star is y by L, u star is u by u naught. Note that we don't know what u naught is, it's still an unknown reference velocity, and v star is v by u naught. So that will be t minus t infinity by ts minus t infinity. So that's my definition of all the dimensionless quantities. So now I can convert all these model equations into the dimensionless form, and so that will be something like this. So that will be u star du star by dx star plus v star du star by dy star, that's equal to beta gravity will be ts minus t infinity into L by u naught square into t star plus 1 by Reynolds number into, based on the length, into d square u star by dy star square. Okay. And the temperature balance will be u star dt star by dx star plus v star into dt star by dy star, that's equal to 1 by REL into Prandtl number into d square t star by dy star square. They are not very different from what we saw in forced convection, except that you've got this new dependence of the velocity on the local temperature, and that's because of the density gradients, and that's because of the body force that we have included in the model equation. Okay. So now they are coupled now. In the earlier case, the momentum balance and the concentration and temperature equations were decoupled. So we could solve the velocity profile independently with respect to the temperature, and we were able to get the gradient. We can't do that here. Okay. So still you can still solve this problem by some transformation. We are going to see that in a short while. So before we do that, let us look at this expression here in which is a coefficient to the local temperature. So that's beta times G into Ts T infinity into L by u naught square. So, we still do not know what u naught square is. Remember that it is an unknown reference velocity. So, therefore, we define a new number called Grashof number, okay, which is not simply the coefficient. So, in all the earlier cases, we attempted to define a dimensionless quantity for the coefficient, and here we distinguish the effect of different forces here, and similarly we are going to distinguish the effect of different forces, and the way to do that is you multiply it by the square of Reynolds number. Okay, so remember that u naught L by nu is nothing but Reynolds number based on the length of the plate. So you multiply it by the Reynolds number. So you get an expression which essentially gives you the ratio of, can anyone guess? Ratio of beta times g, what does it signify? Gravity. So it's the buoyancy forces or force that the fluid is experiencing because of gravity. So u naught square will cancel out. What does nu signify? Viscous forces. That's all. So it's very easy. So Grashof number, which is essentially beta g T s minus T infinity into L by u naught square into REL square. Okay, so that's the ratio of buoyancy forces to the viscous forces. Yeah, but it's just some function of viscous forces. So it's a square. So you will have square of the viscous forces. That's because of the scaling that you will require for the buoyancy forces. So that gives us an interesting framework to answer the question that we posed a short while ago. How do we decide whether the free convection or the forced convection is the dominating mode of heat transport? Okay. So Grashof number by REL square. So that provides the framework for understanding which one is the dominating mode of heat transport. Okay. So supposing if you have in a real system, so real system, the bulk velocity or the free stream velocity is really not zero. So if you use the free stream velocity for a real system as the scaling velocity, so Grashof number by square of Reynolds number gives you a dimensionless quantity which can be used to decide which one is a dominating force. Okay. So supposing if it is this much smaller than 1, okay, what would you infer? Which one is important? Forced or free convection? The forced convection which is important. Forced convection dominates, and if it is much larger than 1, free convection dominates. Free convection dominates, and if it is almost equal to 1, then you would expect that both are important. Both are important. And what if it tends to infinity? So look at the ratio. U naught tends to 0. So that's a purely free convection problem, right? So that's a purely free convection problem. So this, when it goes to infinity, it simply means that the bulk Reynolds number goes to 0, which means that the bulk velocity is 0, which is the definition of free convection. So we started by assuming that it's a quiescent fluid. So when this tends to infinity, it means that the Reynolds number is 0, and so therefore the bulk fluid is at a rest, and so it's a purely free convection problem. So it just provides a framework to decide. Note that in a real system, you're never going to have a completely free convection mode. There will always be some disturbances. Even in the coffee cup example we saw, there will always be some disturbances. You are going to have airflow, you are going to have a fan, so all that is going to disturb the fluid. So therefore, it gives you a nice framework to decide which one is the dominating mode of heat transport. Okay.